All right, so today, this new chapter is chapter 13. Lucky number 13 is about estimating ideas, estimating numerical quantities. Lots of important topics, and that's probably important. So, yeah, let's get on into it. So, please start reading chapter 13. Um, you'll see very similar things to what we talk about. Also, I want to talk about your next project. So project 2, so we had project 1 only. There's 3 projects in the class. Project 2 is the next one, and I would like to schedule a due date for it right now. It needs this chapter, but you can already get started because it needed previous chapters, but like this is the last one that it depends on. But you can do kind of the first half of it. So I'd rather you get started than not get started. So let us go down to that so you can have it because I need to release it. That one I didn't just automatically release. And let's think of a good due date. So let's see. So we got spring break. I'm not going to have anything due spring break. I know that I assigned or I made some due dates for the something last time. So it needs to be after that for sure. So this is April. Okay, so yeah. April, we've got the 8th and the 10th. So yeah, I think maybe a good due date would be, let's say the 17th. I think that might be a good time to have project 2 due. It's like a Friday, so a decent amount of time because it is a good chunk of a thing. And there will be time to finish this chapter as well. So let's plan on the 17th for project 2. And remember that for projects, you can, if you want to, you can work with a partner, right? So do consider that if you would like, but that's when it will be due. And yeah, that should be okay now. It's released and you have a due date on it. Okay, back to the other stuff. So you can do about half of it right now, but we will even more after today, that's for sure. So yeah, the first thing I want to talk about is a concept called a percentile, which is probably a thing that you've learned before, like you took at least in like grade school, right? Elementary school, middle school, and high school, you did like your standardized testing, and then they send you and your parents your scores, and you're like, you're in the something percentile, right? So you've probably heard that word before. Let's talk about exactly what that means. So if you are in the pth percentile, where p is a number, like you're in the 90th percentile, that means the pth percentile of a bunch of numbers. It is the smallest value in that bunch of numbers, think of it like an array, that is at least as large as p% of all of the values. So that's a little vague and confusing. But if you are in the 10th percentile, that means you're at least as big as 10% of the numbers in the data set. That's what that's trying to say. That's the 10th percentile. If you're in the 90th percentile, that means like you scored better than 90% of people. That's kind of how that means for test grades, right? You're at least as large as p% of all of the values. If you're at least as large as 90% of the values, if you're in the 90th percentile. But it's the smallest number for which that is true for us. Okay, so there's the concept of small and big together, which is a little confusing. But yeah, here's one way to find, if you got like an array of numbers, here's how you find the pth percentile. Like I want to find the 90th percentile. I want to find the 12th percentile. There's a few different algorithms, and the one that the book is going to teach is probably the easiest one. It's called the nearest rank one method. So what you do if you want to find the pth percentile of a number, like the 75th percentile of a number, you sort them because they do need to be in order so that you can see like how many are bigger than this, how many are smaller. And then you find that much percent, p% of the number of things that you've got. If you've got n numbers, find p% of n, which is just like p over 100 times n, right? Give that a name, call it k. And that's kind of like an index, right? That's like an index at that point into your array, more or less. If it's an integer, take that element. Which is really, it's not quite an index, right? So it's an element at index that minus 1, because the first thing is not index 1, it's index 0. Otherwise, you'll round up and go to that number. Okay, so that's just a bunch of words. Let's figure this out. So let me show you how to do, let's find the 70th percentile of these numbers. So they're already sorted, 6, 7, 9, 12, and 17. All right, it's going to be 12. The 70th percentile of this one is going to be 12, and let's talk about why. Okay, let's figure it out together. So the very first thing we're going to do is figure out, like, how big is this? How big is this sequence? It's size 5, right? So n is 5. N equals 5. And so the very first thing we'll do is, after that, is we'll find 70% of 5. Yeah. So that's, let's see. What's a good one to do here? Yeah, we'll do 70 over 100 times n, which is what? Let's figure that out. Dun, dun, dun. 70 over 100 times 5. I need to import all this stuff first before it tells it to me. 3.5. Okay, so that's going to be 3.5. And this is almost a number, right? We're kind of using that as an index eventually, but it's not. It's not a number. It's that number is not a whole number yet. It's not an integer. So if it was, we go to that element exactly at index that minus 1. But otherwise, we'll round up. So we'll round up to from 3.5 to 4. So we want to go to the 4th element in this sequence, and that's going to be our 70th percentile. Okay, and that is for us index 3 because it starts at 0. So that brings us here, right? So that gives us the 12. So 12 is the 70th percentile. It is the smallest number that's at least as big as 70% of the numbers, all right? Because 70% of the numbers would be like 3.5 of the numbers, which doesn't make sense. You have to, like, you got to round up, all right? So this is the number that's bigger than or equal to 3.5 of the numbers, okay? So yeah, that's how you find it. Does that process kind of make sense? You just go into a place in a sorted array. This is also, right, 12 is also the 71st percentile, the 72nd, it's also the 80th percentile because there's not a lot of numbers. So when you have to, like, round, that happens too. So what is this? 80 over 100 times 5. That is legitimately, what, 4/5 times 5, so 4. That's like 4th element all over again. 4th element. Index 3. So if you have a small sequence, some of the percentiles are going to be the same because, like, this one's as big as at least as big as 70% of the numbers. It's also at least as big as 80% of the numbers. It's the smallest number for which that is true. Okay, that's how you do it. So I think that's more or less what I wanted to say. If you wanted to find some other things, that's kind of your process. So let me give you this, and I'll have you try. So here, question for you. With this in mind, here's your process. Try to find the 30th percentile of these numbers, and then also the 45th percentile and the 89th percentile. So this is your list of numbers. You can break out Jupyter, and you don't have to write this down anywhere. I just want you to try it. So try to find all of those percentiles of that set of numbers. I'll give you a few minutes to try it. So what's the biggest number that still this works for? So what's the number that is at least as big as 30% of the numbers in this sequence? It's the smallest one for which that is true. Because, like, the last number kind of, if that wasn't your side condition, the last number would always be the thing, right? It's like 24 is at least as large as 100% of the values, right? But that's not useful information. You want to find the smallest one that works. Mm-hmm. Did I give you these numbers already sorted? Yes. Yeah, try each of those. All right, that's enough of a head start for me. So let's try these. Let's try these together. So we've got, first of all, how many numbers are here? 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. So n is 9. That's going to be useful for us. So if we want the 30th percentile, we want to find 30% of 9. Well, what is that going to be? I want 30% of 9. What's that going to be? That's going to be 30 over 100 times 9. And that's like 2.7-ish. Well, that's exactly 2.7, actually. It's just, it couldn't fit properly into a float. And so this is not a whole number yet, so we're going to round up. We'll round up to be the third element, which, remember, that's going to be index 2. And sometimes I abbreviate index as just IDX for short. So index 2. So 0, 1, 2, that makes this the 30th percentile. It's the smallest number that's bigger. That's the smallest number that is at least as big as 30% of the values. So yeah, I think that is most of what I wanted to say. And then the rest are going to be similar. But do remember that certain percentiles are kind of all equal to each other. Like which of these values is going to give us the fourth number? There's a couple of them, right? There's going to be quite a few of them. So there's a few different options. So this is not only the 30th percentile, it's probably also the 31st percentile, for example. So you got those going on. And yeah, I think that's kind of what I wanted to say. So this is like 3/9. Because what is this index going to be? This is at like 3 out of 9. Index 3 out of 9. That's like the biggest that it can be is like the 33rd percentile, right? All the way to what would be the other one, the one at the index that was before it. That's like index like 2 things. That would be 22% exactly. So from 22% to 33%, that's this one. That kind of makes sense. It's going to be between the two of those. And so those are all the percentiles that are between, like that make up this index, as long as it's strictly bigger than 22.2. So yeah, that they share. Some of them share a bit. Let's do the same thing for the 45th percentile and the 89th percentile. So what's the 45th percentile? 3. All right, what's 45% of 9? Which index? It is not 4, it is 5, right? Got to round up even if it's 4.05. So index 5, or the 5th element, sorry. The 5th element, which is index 4. So 0, 1, 2, 3, 4, that's going to be our 45th percentile. Does that make sense? Questions about that? I'll always give you the smallest number in the sequence, the smallest place in the sequence that holds the element that's at least as big as that many percent of the numbers. Okay? 45%. And then 89th percentile, let's go figure that one out too. That's going to be, all right, what's 89% of 9 elements? It is 8.01, so not quite 8. So that means we need to go to index, we need to go to the 9th thing, which is going to be index 8, which is the last thing. So this number right here, just barely, is the 89th percentile. And then, of course, this last number is everything, right? 89th percent, all the way from that to, because it would have been 8 out of 9. The previous one was 88%, 88.8%. That was this element. That was the biggest one that it worked for. And then this one, 89th for sure, onwards to 100. This is also the 100th percentile, right? So the number that's at least as big as 100% of the values. Okay, so that's all a percentile is, and now we know how to calculate them. Yeah, any questions about that? See the process? Luckily, we don't have to do this ourselves. So in our data science library, there is a percentile function. It's right here. You give it, you just say percentile, and then you give it what percent you want as a number between 0 and 100. It's not like just like a ratio. It's not between 0 and 1. 0 and 100, it's like 50. I want the 50th percentile, the 90th percentile, okay? Because it's in percentages. And then you give it a big array that doesn't have to be sorted. It will just deal with that. It'll figure it out itself. And that's how you do it. And then it'll give you back the element, the number that is that percentile thing. So that means, let me write this just for posterity, there is also a percentile function. And then here's how you use it. You can say, I say percentile. Which percentile do I want? I want the 30th percentile. Of which numbers? These numbers. Cool. And then it finds it. That was the number 12, just like we found. So it'll do it quickly for you. It doesn't have to be sorted. This array will just find the right one. It'll sort it itself under the hood, kind of. And then 89th percentile, like it'll find the right ones. So yeah, that's what I wanted to, yeah, that's what I wanted to say about that, I think. Questions about how to use the percentile function? Oh, not too bad, right? Self-explanatory. Let's see. How do I want to do this? Yeah, percentile does not require sorting. Let me prove that too. Let's say you got a bunch of numbers. I'll call them nums, and they're out of order. Because in your data set, you're not going to have things in order usually. And then, so that's your thing. If you want to sort something, you can. It's np.sort will do that for you. And then nums. It gives you back a sorted version of the thing. It does not update the nums array. So you can assign it back in if you want to, but np.sort will sort the thing for you. And so you can for sure give the sorted thing to percentile. What was the 75th percentile of this? It's 8. But you could also have just given the original thing that was unsorted. The percentile function will deal with that and find the right thing. Okay? So that's all I wanted to say about that, I think. So yeah, with that in mind, let's talk about some special percentiles, because 75 is one of them. All right? They're called quartiles. These are important percentiles. All right? These are like numbers that kind of balance the elements of your sequence. So the first quartile is the 25th percentile. It's like the thing that's it is the smallest number that is at least as big as 25% of all the values. Okay, and so that's a nice balance point there. That's the first quartile. The third quartile is the 75th percentile. So that's how you find that one. And then the second quartile is the 50th percentile. It's the number that is at least as large as 50% of the elements, half of them. We have a word for that already. It's called the median, right? That's another name for the median. So let's talk about that. So those are important numbers. Like this is really me finding the third quartile, right? The third quartile of those numbers. So yeah, I think that's most of what I wanted to say. So if you wanted to find the third quartile, it's the 75th percentile. If you want to find the first quartile, the 25th percentile. It's apparently 3 for this data set. You did learn in math class though. Quartiles are kind of different. You did learn that median, for example. You remember how to take the median of an even list of numbers, an even size list of numbers? It has to do with you finding there's no middle element at that point, right? There is no middle element. And so you kind of have to average the two together. Let me show that to you. So let's say you've got this data set. 1, 3, 5, 7, 8, 10, 11, 11, 15. So I don't really know where the middle is. Let's find it real quick. 2, 4, 6, 8, 10. So it's the fifth, right? So here, 1, 2, 3, 4, 5. These are the middle elements, right, of the sequence. There is no true middle element of an even-sized array. And so when we learned how to find median in math class, it's going to be 7.5 because you take the average of the two, right? Percentile, the percentile function is lazy. It's going to do this kind of calculation, and it's not going to give you the 7.5 like you might think. It's going to give you, but for big enough data sets, it's not going to really matter too much. It's going to give you the 7. So the percentile function does not do the fancy kind of median calculation. There is np.median that will find like the true median and use the rules that we learned about in math class. But the percentile function is a little bit lazier, okay? It's a little bit lazier because of that. So in theory, all of these quartile calculations are supposed to use the special rule, like you average the two things in between if there is no quarter element, middle element, three-quarter element, like when things are even-sized. But the data science library with its percentile function does not give you like the true median back. It's going to be a little bit lazy. It's going to use the formula that we talked about, okay? So yeah, it's up to you, like, and your use case, like how accurate do you want your thing to be? So you get like, I guess I want you to try this. So if you get an even size sequence, it's like, do I want the true median, or do I want just the 50th percentile? It's close enough usually. Depends on what you're doing though. Okay. So with that in mind, I tried to calculate the first, second, and third quartiles of this sequence. Can you find them? You don't have to write it down anymore, but I want you to just practice the idea. So this is an even size sequence. What will it be? What's the number at the first quartile, second quartile, third quartile? When you do like chop it in half, you know where the middle is, right? You can think of the first quartile as the median of the first half numbers. Yeah. You can think of the third quartile as the median of the second half of the numbers. That's an easy way to find it, maybe. So it's just secretly medians. Because the first bit, the second bit, just like chop it in half. If I go back to this picture really quick, you can see that, right? You chop the first thing in half. There's the first half. The median of that is the first quartile, for example. All right, do you see it? So there is no true middle. So the second quartile, which is the median, is going to be like the fancy mathematical definitions. It's the average of these two, right? So like 6.5. But if you use the percentile function, you want the 50th percentile, you'd go, all right, what's 50% of 6? Because there's 6 elements here. That is 3, right? And so the third element is the 6. So that would give you the smaller of them if you called the percentile function on that. Or the 50th percentile. So either one of those answers I'd accept on like a test or something. It was 4, 5, 6, 7, 8, and 11. So yeah, the percentile function will just give you the 6 because of that calculation. But what about the others? What should the first percentile, or sorry, the first, not percentile, what's the first quartile? What do we get? Because the first quartile is just the median of the first half. What would the median of this be? You see it? this is now, it was an even sequence before, but now it's odd. Now it's odd. There is a true median, right? And there is a true middle point. So the first quartile then is the median of the first half, right? The first quartile is the 5. You see that? I'm just shy today. You gotta tell me if you don't understand. So that's the 5. And then that implies that the third quartile, the 75th percentile, right, is going to be the middle of this, the 7, 8, and 11, which is just the 8. And I think that the percentile function should agree with that too. So that's pretty nice. So those are just fancy special cases of percentiles. Those quartiles are important because they kind of show you interesting facts about the numbers, how they wrap around, or how they look. I think that's what I wanted to say. So that's quartiles and percentiles. Any questions about those concepts? So we're going to need them. All right, I want to teach you a process then. A process of estimating values. Because we're never going to get the whole thing, right? We're always going to take a survey of people. We're not going to get like an entire data set of the population data because that's really hard to get a lot of the time. So our goal, right, parameter versus statistic, we have a population that we care about, like California voters, because we're about to have elections, right, or US voters. We'd like to know the value of a parameter, like, I don't know, what percentage of votes is this candidate going to get or something. Or what's the average age of users who are going to enjoy this TikTok that TikTok is trying to show you right now. So if you had a data set for the whole entire population, that's a census, if you had that, a sample of the entire population, then you're good, right? You can get the actual true value of the parameter because you can just calculate it from the data, right? You can just like, okay, show that video to every single TikTok user and figure out, all right, all of their average ages, because surely they know that secretly. And that's not possible, right? Some people aren't going to log on and look at it. So you have to estimate, right? You always have to estimate the parameter you want, this average age, this percent of voters who are going to care about this candidate. You estimate your parameter with the statistic. You took a smaller sample, one that you were able to get, and then you estimated the parameter with the statistic. And if you took a good enough sample, right, the statistic will be a decent way of inferring that parameter, okay? So that's how that works, right? So if you don't have a census, which you probably never do, you got to take a random sample from the population because that kind of averages out any inconsistencies, and then you use a statistic. So take the average again, but of this smaller sample, and that will give you an estimate of whatever your parameter was, all right? So that's what you want, and that's kind of what we've been thinking about, right? But now the question is, you've taken this, you've gotten this data, you've taken a sample of all these TikTok users, and you showed them this video, and you've averaged their age. You've got a number, right? You've got a number, and the question is, how good did you do? Right? Because maybe you accidentally, randomly picked too many old people, right? Or too many young people. Like, it wasn't a good random sample. This is never perfect. So your estimate of the true value is never going to be perfect. It's never going to be the exact true value, but it's going to be maybe close, right? It's going to be inexact. So the question again is, how inexact? Could we maybe calculate a range for where we think the real value is? That's where we're going, all right? That's what this chapter is about. So yeah, again, the name of the game is we have a giant population. We need to know something about that population. We want a parameter, but we take a sample instead and use that to infer stuff about our population. But it's never perfect because a sample is not the entire people, right? Not the entire population that we care about. So yeah, the idea is we could have taken a different sample, right? We could have had a different group of people watch the TikTok. We could have texted a completely different group of people asking who you're going to vote for, right? And you would have gotten a different answer. You would have gotten different values. Maybe they'd be close to each other decently, but they would still be all over the place, right? At least a little bit. So the sample statistics for each of your samples that you could possibly take are going to vary. We want to know how much they might vary. That's the question. So like what we would like to know, we'd really like to know, like how different would our estimate be, right, for our statistic? how different would that be if we took another sample? We went out and we called a bunch of more people. We went out and we showed the TikTok video to somebody else, a different group of people. And because it could be different each time, our question now is like how accurate is the estimate that we're creating? So that is where we're going, and I hope you see that is a useful thing to care about, right? Because you're never going to get the right answer because you just took a sample. What would happen if you took a different sample, right? How might your estimates change there, all right? So that's where we're going, and one way to do this and try to simulate, because the goal of this class is to use simulation to kind of answer these questions. There is a true mathematical way of doing this in statistics that maybe you've learned about, but the way that we're going to do this in this class is called bootstrap sampling, all right? Because what we'd really like is we'd like a bunch of different surveys to be given out to people. We'd really like a bunch of different people. We'd like a bunch of different samples so that we can compare, like, what are the different values that we could get. But that's pretty much impossible, right? You can't go and call 1,000 more people because that would take a lot of time and money. So we would really like to get a bunch of random samples. Right? If we want a bunch of different values for our estimated parameter for our statistic, we need a bunch of random samples, different ones. But we can't go back and sample again, right? We cannot go and ask a few more people to watch a TikTok. We can't go and call more people on the phone and ask them who they're going to vote for because maybe like the election is in an hour. We don't have any more data. So like there's no time, there's no money, usually is the problem. There is a way to simulate random sampling with just the sample that you only took, right? Your one good sample that you got from your population, which is crazy to think about. It's called bootstrapping. You're using that one sample that you took to create a bunch of simulated samples, right? That's kind of nice. So yeah, in theory, your original sample that you took, the one that your company paid a lot of money for to go off and call these people and interview them and ask them things, and you got a number based on that. You have data already. You have in theory, a nice random sample that's pretty big, and so that random sample decently represents the population that you're sampling from, and so our goal is then to get another random sample from our original random sample, all right? And that's what bootstrapping is. So the way that you do that is you take a random sample from your original sample, not without replacement, this time with replacement, okay? So this is kind of what bootstrapping is all about. You got your original data with a bunch of different values. What a bootstrap sample is you take that random data and you sample just as many things again to create another same size data set, but you do it with replacement. Because maybe if you sampled too many old people, this will clone some young people in your data set with replacement, right? And then that might be a little bit more accurate. Same with this one. Maybe you sampled too many young people. This one, if you do it again, maybe you'll get a sample that cloned more old people, and so it kind of averaged it out because you do it with replacement. So you create a sample that's similar yet different because it's with replacement, but it's the same amount of elements, all right? The same size data set. That's what bootstrap sampling is, and that's kind of cool to think about. I'm going to show you an example of that once I explain it, but let's see. Do I want to do that now? I guess. So here, let me show you that bootstrap sampling works. I've got a data set, all right? And this will help explain it to you. So I have a data set about, here, let me just read it. Read table data. It's called San Francisco 2019. And what it is a bunch of employment data. So here, this is the city of San Francisco in 2019. We'll call it population. They published, let's do like sample 10. What they did is they published a data set of every single worker in San Francisco that worked for the city. And they told, like, each row is a worker. So they tell you their organization, their department, their job family, what their job title was, what their salary was, how much overtime they made, how how much their benefits cost that were part of their compensation package, and then they add them all up into total compensation. So you've got compensation data for every single public worker in San Francisco. All right. This is legitimately a census right now. This is something that we wish we had. All right. So we legitimately have population data right now. What I'm going to do to show you that bootstrapping works is I'm going to take a sample of this data to pretend that we only just interviewed a few public workers from San Francisco. And we're going to notice how similar it was to the original data. Okay. That's what I'm about to do. So we really have our pie in the sky dream right now. We have a population data. We have this right here. So this is almost never possible, but I'm going to use this population data. I'm going to take samples of it so that we can see that bootstrapping works. All right. It's almost never possible to get this. So this is a great example so that I can show you exactly that this will resemble the true population. It's almost never possible to have the entire population, but we're going to practice with, all right, practice with one. All we usually get, right, are samples. So maybe our goal is like, what is the average total compensation of a public worker in San Francisco who works for the city? We can actually calculate that number right now by using our data set. But what if you just went out on the street and interviewed some people who worked for the city? How close, you took a sample, right? How close would it be to the true value? That's kind of what we care about right now. So yeah, let's explore this data set. It's kind of cool to think about. So there's a few different values here. Population.sort. One interesting thing about this data set, descending equals true. Some people did not, like this is, oh yeah, here's like the top workers. We'll do it the other direction in a second. But let's see here. Here are the top workers. The chief investment officer made $725,000 in 2019. Good for them. So that is, yeah, that's like, these are the highest earners in San Francisco who work for the city at least. And we can do a histogram because this is like, these are for sure large amounts of money that not most of the workers make. So we can do a histogram of this. We can do population dot histogram on total compensation. And let's do these bins because these are good amounts of bins. So let's go up to 600,000 because like this one is the only one above. Like these three are the only ones above 600,000. So let's just cut it off there. Let's go by intervals of 25,000 for our bins for histogram. And then here it is. We know that there was people over here, but there's just so few of them that we don't see this at all. It's thinned out. So we have this histogram where I guess a decent chunk of people are making a little over 100,000 in 2019. Because it's an expensive place to live, right? But you also have this giant spike. That's a small number. Were these a bunch of interns? What is this? So we do have to explore the data to figure this out. Because we do want to calculate something first. And so if you look, some of these job titles have zero total compensation, a lot of them. So I forget exactly what this means. It could have been that these are just unfilled positions right now. Nobody's working. Or this is like the second, like somebody works in two capacities and like this is their other title, but like they don't make any extra money from that title or anything. Like they get the pay that was from their original title and all that. So like for some reason, there's a few people in this system or jobs listed in this system that have zero total compensation. And so if you do an average of all this, these are gonna weigh it down because these aren't real people. All right. So we're gonna have to let's omit that. Let's omit those things. So like because we care about like full-time workers, let's say. We care about the full-time workers in San Francisco and we want to calculate some data on them. Let's say that that's the survey. We're surveying full-time city workers. So let's calculate like, all right, if you were a full-time worker, how much money, like what's your minimum salary? Like because we got to do above the zero stuff here. So what's like the min salary that you would have if you're a full-time worker for the city, making the like minimum wage. So in San Francisco, we had to look this up. In San Francisco, in 2019, the minimum wage was $15. And let's say that, I don't know, we don't have to do 40 hours. Let's say that they're at least part-time, right? Part-time, so 20 hours a week at least, and they use 2 weeks of vacation, which is unpaid. Let's calculate what the minimum salary of people I care about asking stuff about is. So $15 times 20 hours a week part-time, and then there's 52 weeks in a year, and if they're using 2 of those for vacations, be like times 50. Let's say that's the min salary that I care about. I don't want to interview anybody who makes less than that. All right, so let's turn that into our population data. We do population where the salary values are above or equal to, right? Above or equal to that minimum salary. And this would give me the data set that actually has normal numbers here, okay? So let's just call that population. Let's call that population now. I'll overwrite the other one, okay? And so that's what we see. And now if we do a histogram, because we've gotten rid of this spike around 0 because it didn't really make sense in the first place. If we do a histogram now, this looks more normal, much more normal. All right, so like some people don't make a lot because they're part-time workers, but the bulk of them are around here. All right, a little over 100,000. So like that is a normal value. And so maybe what we care about, let's pick a statistic, or not a statistic, let's pick a parameter, because this is population data right now. This is everybody, legitimately everybody. Let's say that we care about the median salary, the median total compensation. So that would be, you can do np.median, you can do the 50th percentile, right? 50 on the total compensation column, right? Because if it just needs an array of data, so total compensation column is an array of data. Just like that. And that's like our population median. And you do know that percentile, this function doesn't really, if it's an even number of things, it doesn't do the average of them in the middle. But you could have just as easily done np.median. So you could have done that, and it is the same value this time, so that's nice. So np.median works too. That's quite nice. And okay, our goal, or the idea, is I'm going to try to show you that this bootstrap sampling idea works. I'm going to show you that if your sample is good enough and it resembles the population, then you can resample and you get better data that way. So we have population data right now. You usually don't. So let's pretend. Let's pretend to make a sample here. Let's pretend that we're surveying public workers in San Francisco who work for the city. Let's say that we don't have all of this data at our fingertips, all these like 37,000 rows of data. Let's say that we interviewed like a couple hundred people, because that's usually all you can do, right? So let's pretend. Let's pretend we took a sample of 400 people, and that's all we have. Because that's usually what's going to happen, right? I'm gonna try to show you now that even if you did that, it's going to kind of match, right? Think of this as the population histogram. This is what we'd really like to know about, like what are their salaries and how do they how does it look? So let's do the same. Let's make a random sample, right? So my sample size is going to be 400. I'm going to say population dot sample, that many things, sample size things, and I'm going to say with replacement equals false, because I don't want to like clone any people right now. So I want 400 separate people that I just interviewed off the street. So I'm simulating us doing a survey, all right? Just to prove to you that bootstrapping is going to work. So this is my sample, all right? So I can now do a histogram of that sample, all right? It's not population more, it's just a sample. This is usually what you have, and the question is like, how close is it to the original thing? You just took a sample of 400 people. This is what the values look like. This is what their total compensation looks like. If you interview just 400 people, and then how does that compare to the original one? It's not horribly far off. You see that? It's not horribly far off. It's decently close, right? You see that it goes up and it goes down in kind of the right places. Some of the bars are a little wonky, but there's not too far off, all right? It's not too far off. And yeah, so that you may ask the question, all right, I took a sample of people. What I really was after was the median total compensation of everybody ever. I know that the true value is that. What is it for my sample? Right? You can do that. You can be, all right, what's my sample statistic, right? Because this is the parameter. What's the statistic? If I took a sample, go to that column. This time it's 138,166 versus 135,747. So it's not the same. It's not the true value, but you see that it's not too far off. It's a few $1,000s off. So maybe you accidentally sampled a couple more higher earners, something like that. But it's decently close, all right? So yeah, usually when you take another sample, it'll look different again, right? So and it's hard, right? It's hard to do it again. So if I do this again, let's get another sample, because most samples will look similar yet different, right, to the original population. So I'll call this sample 2. We'll do a sample 2 histogram. We'll get the percentile for sample 2, the 50th percentile. So I'm doing it all over again. And like these are 2 samples of the population. Because if you were to survey people again, like you get a different 400 people, right? You do that again. And so that's what that looks like. And this time, your estimate of the median compensation for these people is a little bit less than the last one. Like this one was 138,000, this one was 130,000, but the true value is 135. So do you see how it varies? If you took another sample, it's going to vary. It's going to be different. It's not going to be exactly the right answer, but it's going to wobble around the right answer, all right? Because if you took a random sample like we're pretending to do, it will work out, okay? So the idea is you took one good sample. That's what bootstrapping is about. You took one good sample. You can't go out and interview anybody else. It's too costly to do that. So you're going to simulate more random samples because you know that if you took another random sample, you get more values. So go simulate more random samples by sampling from your sample. That's what we're about to do. That's what a bootstrap is. Sample from your sample. And that should give you different data again, right? Because it's going to clone certain people and like cross out other people. And so it'll give you different data based on your original sample, and that will lead you to conclude some stuff. All right, that's our goal. And this is kind of the process. Like we usually don't get this. We wanted to know what the population data looked like. We usually don't get to see this, but for this example, we had it for fun, just to practice and understand what's going to happen. Usually you took one good sample. Like it looked like that. It wasn't perfectly representative of the population, but it was close enough. And then what our goal is to sample from the sample. That's what bootstrapping is all about. We're going to sample from the sample to get a bunch of, they're called resamples. And it will look a little bit different. They'll all look a little bit different because they'll clone some people, and not clone other people. And you can calculate more median values, and the values of the median will vary because you have different data sets now. Secretly, data sets, different. And that will help you see how, like, what would have happened if you did actually go out and take another sample in the actual population. So because of the law of averages, which you hopefully remember that idea, it's like you used enough things, right? It all works out in the end. It all averages out in the end. If you started from randomness and you had enough numbers, these will eventually like look like the original population. And if you do it enough times, it will kind of average out any of the inconsistencies that maybe existed in the sample that you took. All right. So that's what's about to happen. Does that kind of make a little bit of sense? We're going to sample from our sample, and that gives us more pretend versions of our original sample that maybe reflect the population better. All right. That maybe reflect the population better. So yeah, with that in mind, here's the process all over again. So like the idea is that if you sample from your original sample, because your original sample was kind of like the population to begin with, then sampling from your sample is kind of like the population some more, right? It's just like as if you sampled from the population again. but it really only works if your original sample was decently large compared to like how big the population was. And yeah, what you do is you take people, right? You randomly take people, you draw them randomly, take a random sample of the same size as your data set with replacement. So with replacement means you can clone people, some people, which means other people get shoved out. That makes the data set look different. And you keep just as many things, because you don't want to mess with the numbers. Keep just as many values, but the values are going to change, because some people get cloned, some people don't get cloned. So here's like the idea of a bootstrap is like you're pulling yourself up by your bootstraps, which is supposed to be a paradoxical idea. But it's going to work out, all right? So yeah, the size has to be the same, because like, say you were doing like an average or medians or things, like you'd get, that if you took a smaller sample, right, we showed last time that like the values fluctuate more. If you took a bigger sample, the values don't fluctuate as much. You want to not like mess with that stuff. You want to keep the same size sample as the original. Okay, so that's where we're going. That's what bootstrapping is all about. We're going to take samples from our sample. All right, so we've got our sample. Here's like our original sample. Say we only interviewed 400 people out of the 30 whatever thousand workers. We have this data. This is our data. It was nice and random. It's representative-ish of the population. We want to know how it might vary. We want even better samples, so we're going to sample from the sample. We're going to do bootstrap sampling, okay? And so what we'll do is we'll make a resample. That's what it's called. So we're going to sample from our population. So we have our original set. Sorry, we're going to sample from our sample. Here's our original sample. It's got 400 things in it. 400 people that we interviewed and asked what they like, how much they made. To sample from the sample, if its name is sample, you say sample.sample, right? Whatever your table's name was, right? If it was t.sample, right? Just happens to be sample here. You're going to call sample on it, and then how many are you going to take? You want to take just as many as were there, right? At 400 all over again. Or quickly, if you didn't know how many, it was sample.numRows, right? Just as many as were there. You're going to do it with replacement. So with replacement equals true this time. But actually, both of these are the defaults for the .sample operation. So you could have just said sample.sample without anything at all, because the data science library was made to do this for us. So these are actually the two defaults. Like take just as many things with replacement. So you could have just said nothing to sample, because those are the default values. So let's call this a resample. Or let's look at it. Like here's me sampling from the population. It's a little bit different, right? It's cloned some people of that sample. Some it's gotten rid of. So yeah, this is called a resample. And then what we want to do is we want to calculate what we're trying to calculate with that new sample, the sampled sample, the resample. So do percentile 50, because we want the median, right, of resample dot column total compensation. And look, from our original sample, this was the original sample here. The median compensation value was 138,166. For our resample, it was 138,373. It's different. See that? We took a sample from our sample, and so it's going to change the values potentially to better reflect the population. That's what it's all about. If we do this enough times, this will give us some variation to see how it could have varied if we sampled again from the actual population, even though this is just from the sample, all right? So this is called taking a bootstrap sample and calculating your statistic from it. So we're calculating, because it's a median, we're doing a bootstrap median right now, all right? So let's make a function that does that process. Give me one bootstrap median value, please. Sample from my sample. We do these two things. Oops. And then it's going to be return that. So it's first step, draw the bootstrap sample. There it is. I've resampled from my population. And what I'm trying to say here, this would work. Would work here. And then what you do is you return the median of that new resampled stuff, of the bootstrap. Return the median total compensation in the bootstrap sample. All right, so that's what happens, and that's a function that just does that process. All right, so the idea is I took one good sample from my population, that's usually what you only have, right? You surveyed some people, you can get a value, but the question is like, how accurate is that value? Because if I took another sample of the population again, I get a different median. So we're trying to figure out its variability by doing bootstrap sampling, by taking this, resampling from it a bunch of times, because it'll give me new numbers, just like we did here. So that turns into this. Let's make then a bunch. Let's create a bunch of bootstrap samples and see what different values we get for the median, because it'll be different every time. So let's make a bunch of bootstrapped. It's very similar to the last chapter. Sample and the chapter before, medians. So I want to make an array that's empty, and let's say that I want to do 1,000 bootstrap samples. So resamples. I want 1,000 resamplings, and so I'm going to do it in a loop, right? For I n np a range num resamples. What am I going to do? I would like to call one bootstrap median. That's going to give me back some new median that's potentially a more accurate one, right? Based on my original sample. I've resampled from it. And then I'll add that, right? I'll take that and append, right, to bootstrap sample medians. Take that new median, put it there, and say bootstrapped sample medians equals that, all right? And so this will take a while because to do that sampling like we did before, that does take a little bit, but we only did 1,000 this time. And so we've got a bunch of different values now in bootstrap sample medians. These are a bunch of different median values for our bootstrap samples, which is kind of nice. And so let's turn those into a histogram. So bootstrapped, say bootstrapped median table. There's just a bunch of bootstrapped medians. Put them there. And let's do a histogram with like 15 bins. That would work. These are the different values that it took on when we did bootstrap sampling. It will center around the original value that we found, which was, what is it? More or less, at least. Those are 138, 166. Yeah, it's around there. Makes sense. That's where the spike is, at least. And do you remember what the true value was for our population? The true value for the total compensation median was like 135-ish, 136-ish. It wasn't the 138 that we had from our sample. Do you see how that value, 135-ish, is taken on by a few of our resamples when we do that calculation all over again? It's taken on. So that means the bootstrap process, it's going to discover the true value and find kind of like the range where it could have been. Does that make sense? We can plot like as a dot what the true population median was. I don't know why this has got to be like this, but let me type these numbers really quick. How many zeros? 4 zeros. This is just I'm gonna put a red dot for where the true population median was. Cool. Is that red dot right there? So this was our true population median. And you see how when we took a bunch of bootstrap samples of our sample, the original sample median was like way over here, is like 138 or something. We do eventually find the true value by cloning some people, crossing off other people. The bootstrap process makes a bunch of different versions of our sample, and some of them took on the true median, right? Some of them took on a value that was at least very, very close to the true median value. Do you see that that's useful? Are there any questions about this idea? Because these are like estimates. These are new estimates. This is like us pretending to get new samples from our population for free. For free. And sometimes it's going to take on, you see that it will eventually, if you had a good enough sample, it will take on the true value. It may not be in the middle, but it's there. And so the idea is like the spread is important here. Because this is kind of what would have happened if we took a bunch of samples. Like we would have gotten values all the way over here. We kind of gotten values all the way up to here. Like that's, if we took a bunch of random samples, that's kind of what this process is saying. Those are the different values that our median could have taken on. And if our question is what is the true median, looking at this spread usually will tell us with good confidence, that's where we're going, there's a word, with good confidence, where the actual value lied. It will give you a range, like this is a range where the value probably is, and it really was. See that? Even though our original sample didn't have the right answer. It wasn't the true answer. The true answer was like 135, right? Even though it didn't have the true answer originally, if we sampled from it again and again and again, we'll eventually find the thing. All right. So that's where we're going. All right. That is, let's see. Yeah, are there any questions about this process so far? Do you see what we've done? All right. So do I want to show this to you now? I guess. Yeah, let's do that. So kind of the idea is we've got a bunch of answers, right? We've got a bunch of answers for our, let's see, for our medians. And here's kind of what we want to do. We've got this histogram now of all the different values that our bootstrap samples took on for median values. And we kind of know where the values lied because it was a histogram that was kind of curvy like this. It was perfect. We would like to do this, all right? We would like to say, like, we'd like to come up with, like, where we think the range of the true answer is, because usually you don't know the true population's answer. Like we do in this example, just because it was a contrived example that's showing the use of this. But usually you don't know what the true value is, but you would like to have some sort of confidence that the value that you're looking for lies somewhere. And so what you'll do is you'll use percentiles. You'll take the, you'll have this histogram of all the different bootstrap medians. You want to know what the true median is, so you want kind of a range of like what could it have been. And so what you can do is like, all right, let's make kind of a decently wide interval where we think this value, this true median, lives. And so maybe 90% is good enough for us. It's called a confidence interval, because if you take the 5%, the 5th percentile, and the 95th percentile, those will be different medians, right? Those will be different values in our histogram. So will be different things that we calculated. You see how if you said like, all right, the true value is between, like you give this number and you give this number, that's now a range, right? The 5th percentile and the 95th percentile, that's now a range of values. In between, you have 90% of your data that you simulated, right? And so you can say that, all right, 90% of the time, if I did this all over again, the true value would be within this range that I'm about to give to you. That's what you're trying to say here. It's like, all right, that's called a 90% confidence interval, all right? It's called a confidence interval. So you can do 90%, you can do 95%. So we've got a bunch of estimates, right? We've got a bunch of these estimates for medians. They're called, it's in a array called bootstrapped sample medians, just like this. If I go to a couple percentiles, percentile 2.5 of bootstrapped sample medians, and I'll do comma to show a bunch of things at once. And I go to the 97.5 percentile, and I output both of these, I'm going to get two numbers. See that? These are two numbers. And what's between 2.5 and 97.5? I'm centered around, right? This is going to be the middle 95% of our data, right? Middle 95% of our estimates. It gives us an estimate. That's correct. 95% of the time, right? That's kind of how you think about this. Right? The middle 95% of our data is between the 2.5th percentile to the 97.5th percentile, right? There's 90, 95 in between. And that's kind of us cutting it off here. It's like saying, okay, 95% of the time, this is where the true value will lie. Okay? 2.5% to 97.5% is the range we want. All right. That's the middle 95. And that's called a confidence interval. So by doing this process and calculating all these bootstrapped sample medians, we've gotten a range where we can say that we are 95% confident that the true median lies within this range. And is that true this time? What was the true actual median that we get to know secretly? It's 135. Is it within this range? It totally is. So we were right this time. And so usually it's going to be right. And so this is me trying to prove to you that this process works and it's going to give you the right answer. You can't just say this is the right value. You can say this is the range of values where it probably is with this much confidence. Does that idea make sense to us? We're trying to quantify our uncertainty. And percentiles got us there. If you want to be a little less confident but give a smaller interval, you can do like the middle 90%. 90% confidence interval. Once the middle 90%, it's going to be from which percentile to which percentile? It'll be the 5th percentile to the 95th percentile, right? And again, this is going to be a less wide interval, but you're saying the true value is here kind of 90% of the time rather than 95% of the time. Yeah. It happened to have the true value within this one, so we got lucky again. We're not within the 10% where the problem might lie, but that's useful, all right? That's useful. So yeah, let's review this process because it's kind of a neat one. So bootstrap sampling is just like, all right, we notice we'd really like to know how much our values could vary if we took another sample, because usually we just have one. We just have one good sample, and we have one good estimate now of our statistic, but like, what could it have been if we took another sample, right? And so a free way to get more samples is to sample from your sample, because if your original sample was indicative or representative of your population, so will your sample be. And if you sample from that, it should work out. All right, and that's the bootstrap process. You take just as many things, you sample from your sample with replacement, take as many values, and that also reflects the population in kind of a new way, and it's showing you how it could have varied if you took another real sample. All right, it's good enough. And then you can turn that into a confidence interval. All right, so here, yeah, we had the true values, we had the true median here, but we pretended this is our only sample. We took a size 400 sample. This is what the compensation values look like. This was the median compensation for this sample, right? This is what we saw. And yeah, I think that was that. So the way that you resample and make more samples is you sample from your sample just as many things, right? You sample from your sample just as many things. Again, sample.sample could have worked here. So you could have just said sample.sample. With nothing. That'll do that, right? And yeah, then this process is going to give you a median for that new sample, right? It's as if you went and interviewed more people and got different values, and you kind of want to see how those vary. So 1,000 times I did this process, and these are the different values for the median that I found for the resamples, for our bootstrap samples, and this leads to, with confidence intervals, a range of values that the true median lies within. All right, it's our estimate. So if you want to be extra confident, you'll do a 95% confidence interval. You go from the 2.5th percentile to the 97.5th percentile. You'll cut off the values here, and you'll be like, all right, with 95% confidence, the true value for the median of the population is within this range. But we never used the population data. This was just from the sample. We calculated this. We happen to know that the true value is 135,000, and it is within this range. Isn't that cool? That's kind of neat. All right. Are there any questions about this process? You kind of see it coming together? It is a lot of things at once. It is a lot of things at once. So yeah, what I'd like to do is I'd like to give you this code. I'd like you to try it. All right, let me give you everything that we've done. If you go to the code from class, it's going to be chapter 13 file. It should be there now. Oh wait, sorry, I didn't save. So now you've got legitimately everything that I've done. What I'd like you to try is let's do the same kind of thing. Let's do the same kind of bootstrapped process, get a confidence interval, but let's do it for, not for medians, let's do it for averages, for average compensation instead. So crushed ice. Here's my question for you. Or let's figure out what's the population. We still have the population data. Our goal is to see like how close could this have been. So population, let's get the total compensation column again. This is the true value. Let's do the mean, right? So the average. So this is the population mean. It looks like the average salary for the population is a little bit bigger than the median because like some high earners kind of squished it that way. So it's 142-ish thousand. And so that's the true population mean. My question for you is to take another sample. Pretend that you interviewed some people. So using bootstrap sampling and our size 400 sample, you can go back, just rerun this code that I gave you, right? This was me getting a sample of size 400. I called it sample. Using that sample, or the one that your Jupyter makes, because it'll be a different random sample, right? Using that, calculate. Let's do a 95% confidence interval. Not for median compensation, but for average. For the average total compensation. So you'll do this process all over again with the sample, but you're gonna be making bootstrap samples and finding the average. Does that difference make sense? So I'd like you to try that. I'll give you a little head start, but that's what I'd like you to try now. So again, pretending that we don't know the actual population mean, we're going to prove to ourselves that this process works because we do know the true population mean. We're going to try and find what this should be. Try to find that range. What you do is sample from your sample. That's what it means to do a bootstrap sample. So copy my function, one bootstrap mean. Now it's like one bootstrap average. Take a sample from your sample and do that like 1,000 times in a loop like I did. Each time for that new resampled thing, calculating an average value for your sample's compensation. And it's going to vary because you're sampling with replacement. It's going to vary, and that will show you what could have happened if you took another sample, because you don't usually have the population data on hand. So it'll look like that. And then once you have like a size 1,000 array of all these different values that are your estimates for each resample of the average compensation, then you can get a 95% confidence interval in this style, right? This was 95. It's like you find the middle 95% of the data using the percentile function twice. You cap it off on both sides. Does that process make sense? Yeah, so I'll give you a head start. Please let me know if you have any questions. It's always better to try it. So you can mostly copy and paste the stuff that I've done. I'll give you a bit of a head start though. Hmm. Because you know that that sample, that one sample that you took, is not going to have the true population mean in it. It's going to have something that's a little bit off, maybe a lot of bit off, because mean is a little bit more fussy than median. It is not going to be the right value, but it might be decently close. And the question is, or what bootstrap sampling does for us, is it shows us how that value could vary if we interviewed more people. It's a way of getting more samples from an existing sample. Mm. All right. Do you kind of see what you change? Other questions? This is not the world's easiest thing. Do yell at me all you want. That's what I'm here for. But the idea is we had a sample, right? We took a sample. We're pretending that's all we had, just so that we can compare it to what we know is the right answer. We don't usually have that, but this time we happen to have that. So we pretend that we took a random sample, because usually that's all we actually have. If you took that sample and you ask for, like, what was the mean of its total compensation, just do that all over again. It's not going to be the same, right? This time it was 145 rather than 142. Yeah, so it's not the same. But the idea is, if I resample from this sample enough times, it will look more and more like the population. It will take on values that range around this value, and it should, in theory, with a wide enough range, with a wide enough confidence interval, contain this, contain the true mean. Okay, so yeah, let's do that. Let's make a function that gives me a bootstrap, not a median, but a bootstrapped average or mean. Whatever you want to say. So, like, give me a sample from the sample with just as many things with replacement so that it can mess things up a little bit, which is what we want here. And then it's going to be from that resampled thing, give me that column, and then you can do dot mean, or you can do np.average of it. There's a bunch of different ways to get an average, right? Like that'll do that. That'll give me one bootstrapped average value. And if I run this a couple times, do you see how I get values all over the place, not quite the same as the original sample, and not quite the same as the mean, but you see how it kind of wraps around. It wraps around. So if we do this enough times, it will contain, right? This array will contain a lot of versions around the right answer, a lot of instances of sample averages. So I can do this all over again. I can do not bootstrap sample medians, but bootstrap sample averages or bootstrap sample means. Sample averages. Bootstrap average. Sample averages. Sample averages. New average. New average. That should do it, right? So I'm making an array of all these different values. Oops, did I not? Oh yeah, sample averages, sorry. Averages. There. And it's going to take a little bit, but it did it. And then we can do a histogram. Where did I do this one? I guess it was this, right? Make a table. It was bootstrap sample average. Not that that matters too much, but bootstrap sample averages is the data. And let's do a histogram on that with like 20 bins. And this is what we see. And this is what we see. So these are all the different resampled averages for the total compensation. Do you see that it, of course, still has the original samples average kind of in the middle, 145-ish. But do you see that it also has the true population mean sometimes within it? 142 something is around here. It's still there. It's still in there. And so that goes to show that this bootstrap process works. It really will give you more samples that sometimes better reflect the true population. Better reflect the true population. And so if I wanted then a 95% confidence interval, I go to the middle 95 bits of this array of bootstrap sample averages. Here they are. And it's like, all right, I can say kind of what a 95% confidence interval is saying. It's like, all right, go to the middle 95% of this data. It's like we are 95% confident that if we do this all over again, we will, like this range will hold the true value. All right. This range will hold the true value. And so this is like, all right, we are 95% confident that the true average for the total compensation of every single San Francisco worker is between this much and this much. And what was the true average? It's 142. It was within this range. But do you see how this is what gives you like an actual answer? Because it's never perfect. Your one sample wasn't right. It didn't have the right value. But we took a bunch of resamples and it wraps around the right value. So the range is important. The range that we get back now is important. That's what a confidence interval is all about. It's a range where we think the right answer usually might be with some percentage of confidence that we can control. Yeah. And that's, I think, what I wanted to say and end with. Are there any questions about this process? It is a more involved one. I hope you can see that. But it's once you study up on it and like kind of understand what's happening, that like it all works out. So like this picture is kind of what I want you to have in your mind. Okay, this is what the population looks like. We don't actually know. You never know what the population usually looks like, but we got a sample. If the sample is good enough, we can sample from it and get more versions, more pretend ideas of what might have happened if we took another sample. And they really will. If the first sample reflects the population, so will the resamples in new, different ways that will kind of, in the long run, law of averages way, show us what the true values might be. Okay? And I think that's where I want to stop. Are there any questions about that? You kind of see what's going on? Please yell at me if you think of anything. I think that's where I wanted to stop.